Okay, we're going to be talking about chi-square goodness of fit, and thanks to the folks at Statistic, we have a nice problem that we're going to work with today. So if you look here, we're dealing with warm weather in Arizona. We're trying to see if that affects the color of people's cars. We're given the distribution of car colors in North America. So we're given 8 colors, we're given the distribution. And then Cass, who happens to be a person who did this, did a simple random sample of 300 cars in Oro Valley. And these were Cass's counts, 84, 38, and so on. We're trying to see if Cass's counts are drastically off from the distribution of North America, and enough, if it's enough off that we can conclusively say that, hey, the distribution of car colors in Oro Valley is significantly different than what we'd expect in North America. So how we go about doing this? We're going to do a hypothesis test. I wrote a null hypothesis. You notice I wrote out a lot of this ahead of time, save us a little bit of time here. My null is that the distribution of car colors in Oro Valley is the same as North America. I even wrote it out here, just using, terminology or, variables here. Lowercase p, because again, we're dealing with parameters here. Population parameters are always going to be p's. If you're dealing with statistics, it's going to be p hats. So I labeled all the colors here, P1, P2, I noticed I labeled them all with their respective colors. Save myself a little bit of time so I don't have to write out each color by labeling them. And then I just did all these equal statements. Because remember, the null is always an equal statement. You're starting out with, this is what it is. Your alternate is going to be some sort of inequality. So I saved myself the time here. I went with a nice short statement, because I'm just trying to prove that the distribution of car colors in Oro Valley is different than North America. Not specifically which color is different. I'm just trying to prove that in general it's different. It could be one color, which ultimately would be 2 colors, because you end up having a lot more white cars, then obviously that's going to be taking from the distribution of another color. So you figure, I just used white as an example, but typically it'll be like maybe two proportions that are off, or it could be more. It could even be all of them. But ultimately, we're just trying to prove that the distribution of cars is different. I could have followed that with an inequality statement here, saying P1 doesn't equal P 0.23, or P2 doesn't equal 0.18. But instead, I just went with a nice summative statement like this. And you notice I abbreviated a little bit for the sake of what we're doing. Significance level in stats, we usually go with 0.05. That's the one we're going to go with here. Unless specified, 5% is usually your significance level, which means you are rejecting 5% of possible statistics. So you figure, okay, I'm going to take just about any distribution I see, except for like that 5% that is way out there. The 5% that I really wouldn't expect. If I see one of those, then that's going to lead me to the conclusion that the distribution of car colors must be different. Before I run my test, I got to check my conditions, as you know. Random sample, yep, told me it was an SRS. 10%. So I want to see if 300 is less than 10% of all the cars in Oro Valley. I'm going to assume it is for the sake of what we're doing. I don't know much about Oro Valley. I'm just going to assume that they have more than 3,000 cars there. Now for my large counts, remember when you're dealing with chi-square, large counts is going to be 5. It's not 10 like you're dealing with confidence intervals and hypothesis tests with proportions. You want 5 in this case. Why? Reason is you have a lot of different categories in some cases, and if you have 10, you're going to have a really big sample size, and you kind of run the risk of, going over that 10%. Remember, the 10% condition exists so you don't oversample. If you go over 10%, you tend to oversample your population, and your sample no longer looks like your population. So what I did was I started checking them, and then I figured, wait a second, if I just go with the smallest expected count here, like green's only 2%. I did 300 times 2%. I know that 300 times 2% is going to be greater than 5. So I just went with my smallest expected count is greater than 5, which means the rest of them must be. Ideally, you want to do all of them, and I did do all of them on my calculator, but I'll show you that in a moment. Now, the key is I want to figure out how different this distribution is from what I expected based on the distribution of colors in North America. There are a couple ways you can do this. One way is to write out the formula, which I did here. I did the expected count. Whoops, did not want to go with that. That's all right. 84 minus, no, excuse me, not expected. Whoops, it's all right, guys. That's why I have erasers. Here's the thing. In stats, you're going to find this is pretty common. You go with what you observe minus what you expect. Just like z-scores almost, see what you see minus what you expect. I saw 84 white cars. I expected to see 69 of them. I then square that difference and divide it by what do I expect. I did the same thing here with, what was that second color? Black. I saw 38. I expected 54. I square that difference, divide it by 54. The reason you're squaring the differences is so that the negatives don't cancel out the positives. Because if you had a lot of positives, a lot of negatives, that obviously means there's a difference. But if you just add them all up, they'd cancel each other out. And then it seemed like there was no difference. So by squaring it, you're able to keep that difference, whether it's greater than what you expected or less than what you expected. And I did this for literally every color as you see. It takes a lot of work to do that. You don't necessarily have to do it, but it's not a bad idea to recognize the formula, especially if you find yourself having to take an exam on chi-square at some point. A lot of times, you won't have to necessarily even calculate the chi-square statistic if it's a multiple choice question. You'll just have to recognize the formula for it. So I set it up like this. I'll show you how I did it. I did it in my calculator. I like the good old TI. The Graphing Calc 83. It's free. Nice free TI here. So I went edit, and then you'll notice I made my list. First, in my list 1, I did all my observed counts, what I observe. List 2, I did the proportions based on the North American, North American parameter that they gave me. I then multiplied all those proportions by 300, and that gave me all my expected counts in list 3. Then, for list 4, I can show you what I did here. Let's see if I can get there. Awesome. Here's what I did. It's a neat little trick here. I go double parentheses. You might not have to, but so I'm going to go second L1, which is what I observe, minus second L3. That's what I expect. Parentheses. Then I'm going to square that. Then I'm going to close the parentheses. And then I'm going to divide that by list 3, which is all my expected counts. Am I doing that? It said syntax error. I got it the first time. Trust me, it worked. Trust me, it worked. I might have done too many parentheses in this case. Yeah, that's probably what I did here. Let me add one, see what happens. And then divided by second 3. Of course, it's doing this now. I guarantee you it works, guys. You can try it again. I'll do it one more time. Second 1 minus second 3. Square it. Then I'll do divided by second 3. One more time. See, it worked. Awesome. That's the goal here. And then to get my chi-square statistic, I just went stat, calc, 1 variable stats, and then I went second 4, which had all those chi-square values. And that gives me my sum of all right here, that 29.92. Nice, easy way to use your calculator if you want to go about the longer way. I'm going to show you a shorter way in a moment. Now that I have my chi-square statistic, I need my degrees of freedom. Degrees of freedom, these are good to know. You take your number of categories minus 1. And that's kind of like your little error factor. That's typically done with, degrees of freedom. You like to do that. And I had 8 colors, I believe, just to double check. I did. So that gives me 7. And why am I doing that? Because I'm going to show you how I'm going to use these values now. Because a chi-square distribution ultimately looks something like this. Right? Now, ultimately, you figure the more, the higher degrees of freedom, that means you have more, more categories. You can expect to see more chi-square statistics, some more higher ones. So you figure you can, find some acceptable ones here, but we're looking for that upper 5%. That rejection zone is going to be like somewhere in here. That's my rejection zone. If I get anything in there, in that upper 5%, then I'm going to reject my null hypothesis. Now, I'm going to go, let's see, I want to figure out my chi-square statistic, 29.92. I'm going to go second, vars. I'm going to clear all this stuff. second, vars, and takes me all my distribution calculations. Chi-square CDF. All right. I'm going to go from my chi-square statistic of 2.92. I'm going to go really high, upper bounds. I like to enter in all those nines. And then my degrees of freedom, which in this case was 7. And I got something really, really, really low, as you can see. So I'm going to write that out here. I got something really low. It's really close to 0, as a matter of fact. It's probably going to be like way out here. That 29.92, it's way out here. So what was it like? I got something really low. Oh, yeah. Notice how they give it to you in scientific notation. That always throws people off. So I got like 0.00009. Remember, if the P is low, reject the ho. It's definitely lower than 0.05. So what does that tell me? I want to come up with some sort of conclusion. It's always good to write out some sort of summative statement. So since, whoops, that looked awful. Let me try using something a little less thick. Here we go. Since my p-value, and I'll write it out, that 0.00009 is less than my significance level, I reject my null hypothesis. What does that tell me? I have enough evidence to prove. It's always good to write the summative statement, guys. I have enough evidence to prove that the distribution of car colors in Oro Valley, I'm going to just distribute here, of car colors in Oro Valley is different than North America. And I should say distribution is different than the color of, of car color is different than the distribution of car colors in North America. And I'll put that too, because that's a little bit better. So remember, if I had a p-value that was above 0.05, I'd fail to reject the null. You never accept it. Remember, you never accept the null hypothesis, stats students. You never do that. Easier way to get there? Calculator function here. All right, we're going to go stat. We're going to go to tests instead. I'm going to go to chi-square goodness of fit test, GOF. Let's go there. Domain. All right, it's telling me I got to enter in something. My expected is L1. All right, let's see if I can do it in here. Done. My expected is actually L3, so I want to change that. L3. Enter. Done. So observed L1, expected L3, and then I hit enter. And you'll notice my degrees of freedom are a little different here. Let's see what happened. I'll have to double check that. These things aren't perfect, guys. Sometimes when you do something for free, when you get something free, it's not always perfect. So let's see. I have L1. I've got L3 here. Okay. But ultimately, this is how you can get there, even if it's not necessarily working too well for me. This happens. That's why it's good to be able to do it anyway. So you notice I'm getting something a little different here. It's probably because I'm just having some issues with the calculator itself. I can probably do it using a regular calculator. If I had one, I'm just going virtual here, and sometimes that happens. You go virtual and you get something different. These things happen. But ultimately, this is how you go about a chi-square goodness of fit test. And hopefully this helps you in the process of doing your chi-square goodness of fit test. All right, best of luck to you.